Welcome to another Advanced Manufacturing Media webinar. Our presentation today is Beyond Prototypes, 3D Printing Transforms Xerox's Model Shop. Hello, I'm Bill Koenig, Senior Editor at Manufacturing Engineering. Before the presentation begins, I'd like to provide some background on what we will be doing today. Our sponsor is Stratasys Incorporated. Stratasys manufactures 3D printing equipment and materials that create physical objects directly from digital data. Its systems range from affordable desktop 3D printers to large advanced 3D production systems, making 3D printing more accessible than ever. Manufacturers use Stratasys 3D printers to create models and prototypes for new production design and testing, and to build finished goods in low volume. Educators use the technology to elevate research and learning in science, engineering, design, and art. Hobbyists and entrepreneurs use Stratasys 3D printing to expand manufacturing into the home, creating gifts, novelties, customized devices, and inventions. Learn more at stratasys.com. The first person we will hear from is Kim Kaloran of Stratasys. She will provide insight into the company and review what additive manufacturing is all about. Following that, Kim will introduce our presenter, Duane Byerley, manager of Xerox's model shop. He will explain how 3D printing has improved operations of that model shop. He'll also discuss how 3D printing saves time on product development. Kim's introduction and the presentation by Duane have been pre-recorded. While that means any questions you have will not be answered during this webinar, please be aware that you may still ask questions. We'll collect them and pass them along to Stratasys, and answers will be emailed to you. To ask a question, simply use the Q&A box that appears on the right side of the screen. Another housekeeping point. As often happens when viewing videos over the internet, the quality of the presentation can be affected by the type of internet connection you have, the amount of total bandwidth available to you, and the number of people accessing that bandwidth at the time. If you experience difficulty, please let us know by way of the Q&A box. The presentation is pre-recorded but will be with you live all the way through. If you have any questions about any other aspects of our webinars, please email me at bkoenig@sme.org. I'll rejoin you after the presentation with a few concluding remarks. Now, here's Kim Kaloran of Stratasys.
Hello, and thank you for joining us for today's webinar, Beyond Prototypes, 3D Printing Transforms Xerox Model Shop. My name is Kim Kaloran, and I'll be your host for today's event. So first, before we get into today's topic, I wanted to give you a little bit of background about who Stratasys is. For those of you who may not be familiar with our company, Stratasys makes 3D printers and production systems based on patented fused deposition modeling technology, or FDM, that can produce prototypes and production parts directly from 3D CAD data using engineering-grade thermoplastics. We also operate Red-Eye On Demand, which is an online rapid prototyping and digital manufacturing service. And you may have recently heard that Stratasys has merged with Objet, which is also a manufacturer of 3D printers, but they use an inkjet-based technology to create a 3D model. Okay, so I'd like to welcome our presenter today, Mr. Duane Byerley. Duane has over 35 years of experience as a senior model maker. And in his current role at the Xerox Model Shop, Duane builds everything from complicated multi-plate injection molds, tooling, multi-surface CNC work, to welding and sheet metal fabrication. He's also the in-house advisor of rapid prototyping and machine services. In 1998, they bought their first Stratasys FDM system, and over those 14 years, he's been heralded as an industry expert in the field. He was given a Lifetime Achievement Award for excellence in the field of FDM and has been a presenter at the Additive Manufacturing Users Group Conference, as well as SME's Rapid event. So welcome, Duane. We're glad to have you on board for this presentation.
Well, thanks, Kim. Thanks for having me.
All right, so now on to the meat of today's webinar. I'm going to review a little bit about what additive manufacturing is, then talk about manufacturing tools, what they are, how they're traditionally made, and then how making them with additive manufacturing can help processes and what that brings to the table. After that, we'll hear from Duane, a bit of history about the Xerox model shop and everything he's using additive manufacturing for, and specifically the FDM technology. So we define additive manufacturing as a process used to create a part by building it layer by layer from the bottom up. There are actually several different technologies that fall under this category of additive manufacturing. And as I mentioned, fused deposition modeling, or FDM, is one of those technologies, which is what we'll mainly be talking about today. Also, additive manufacturing has many different names, and it's basically synonymous with terms like 3D printing, rapid prototyping, rapid tooling, and et cetera, et cetera. So specifically, we're going to talk more about manufacturing tools. People aren't just using additive manufacturing for prototypes anymore. They can be used for form, fit, and functional testing. They can also be used for manufacturing tools and even low-volume end-use parts. So what we're talking about when we say manufacturing tools or jigs or fixtures is basically a broad range of items used to make products. As you can see on the slide here, everything from patterns like molds, tools, and dies to jigs and fixtures including work holding tools, check gauges, drill guides, go, no-go gauges, alignment tools, assembly tools, and quality control tools, basically whatever tools you're using on a manufacturing floor. And they come in many different materials in all shapes and sizes and range from simple to complex. But all have one thing in common. They're used to produce a quality product as quickly and affordably and repeatably as possible. So let's talk a little bit about traditional processes of creating manufacturing tools versus using additive manufacturing to create manufacturing tools. They're traditionally machined or fabricated from metal, wood, or plastic. Like the items that they're used to produce, these tools also need to go through a design, documentation, and production process themselves. On average, production of a manufacturing tool can take 1 to about 4 weeks. This means that the process can be slow and can be expensive, even if the design is kept pretty simple, which isn't always what's right for your tool. Also, as a part of the traditional process, you need to wait for delivery. Once you get the tool back, you need to inspect it and test it in the manufacturing process itself. If it's not acceptable, you need to make design changes, return to the vendor for a new quote, and start the whole process over again about getting it manufactured and sent back to you. And then you repeat design iterations as required. So given all of this, there are some definite advantages to traditional processes, like it's a proven industry standard. Surface finish is typically very smooth. And at high volumes, it's actually pretty easy to justify the cost. But with all the steps in the process and with so many people involved, it's easy to see why conventional methods for manufacturing tools can be slow and expensive. Another limitation is the concept of design for manufacturing. So when making a one-off item like a fixture, basic machining and fabrication tools are what are available and commonly used. So you're limited to what they can do quickly and affordably. This yields, basically, you have to design for very basic shapes, and these basic shapes are not always optimal for actual performance and weight or worker ergonomics. And this is really where additive manufacturing comes into play. Additive manufacturing offers an alternative method for producing manufacturing tools. Instead of cutting, bending, shaping, and welding a jig or fixture or guide, additive manufacturing constructs the tool from the bottom up using a layered process. It creates just what you need. This eliminates a lot of steps in the process, cuts cost, cuts lead time, and labor hours. It also removes the constraints of how you design the jig or fixture because it is an additive process. So what's involved with making the jigs and fixtures with additive manufacturing? First, you're designing your part in CAD. You're outputting an STL file. There's no detailed drawings required. either get the manufacturing tool built out of house or through your own system, and go ahead and make more than one at the same time. You can fill up the build platform as much as you need. After the build is done, you remove the supporting material, and then you can inspect and test the tool. If it's correct, you send it onto the production floor for immediate use. If it's not correct, you can easily iterate and change your design and get more printed out fairly quickly. In addition, after a tool is created and in use on the manufacturing floor, you'll probably notice reduced worker fatigue due to the lighter weight tools. You can design tools so that the internal structure really it's not a solid fill. It can be a honeycomb structure on the inside to reduce that weight. And you can implement more and more work-holding tools to help streamline the manufacturing process. So the Stratasys manufacturing facility today uses over 350 jigs and fixtures on our production floor, which actually is more than 30% of those jigs and fixtures are FDM. So we're trying to practice what we preach, and it really is worth the savings and the time we're able to realize. So this is enough out of me for now. Let's talk to Duane from the Xerox Model Shop to hear his story and examples of how they're using additive manufacturing today.
In 1998, we started a new printer platform that went from our conventional sheet metal chassis to a plastic chassis that we knew was going to take several iterations to get right. So I started building these on a milling machine, and we started sending out work right and left to the point of at the end of the year, I was told I sent out $1.6 million worth of RP work with, mostly just trial fit pieces. So we realized then that we really needed our own process, and being an engineering background, I want to make sure that it works for us. I want to make sure that the part I'm getting is going to be the same 2 months from now. And so that sort of limited it to FDM and possibly an SLS process. We had a world-class machine shop, and we can knock out parts pretty quickly, but we knew that wasn't always the fastest process. So in terms of the side frames, where I would laminate blocks of plastic together and let it dry and then start carving on it, it would typically take me at least a week's worth of machining on sometimes 6 sides to get things right where I wanted it. In the meantime, I've got 128 engineers who are already doing rework. So by the time I'd get that done, they had 3 revisions that I needed to cut in and glue in and start all over. With FDM, the first thing we noticed is it would take about 40 hours to make an FDM side frame, but that 40 hours was a little over a day. I mean, it was less than 2 days because it's running 24/7, and I don't have to be there tired running a milling machine. When we bought our first one, it was a Maxim, which is no longer made, but it had a nice big build platform. It only allowed us ABS. And in spite of, people maybe wanting a little different material at times, 8 months later it had paid for itself. In 2004, as we were winding up that platform and starting our next one, we added a second machine that allowed us to go to polycarbonate. And at the time, we had PPSF and PCABS. We had several materials that we like to use. It took 11 months to pay for itself, but only because we had 2 of them now sharing the duties. From a tool and die maker standpoint, I make a lot of parts as well, but I kept looking at these FDM parts and looking at fixturing, and anyone that's in the industry knows that fixturing oftentimes is the most expensive part you're going to build because it's a one-off. You're not capitalizing on having the same setup for several parts. You're pretty much into that one part. So I started looking over the fence at tooling and just little things that we did that I saw technicians and engineers coming in trying to push gears onto things that don't stand up, or trying to keep something flat. When you fly cut something, you need to relieve the stress on both sides, so it starts to kind of potato chip, or you try to lay it back down. And what we found with FDM is it's basically kind of put together like plywood in layers, and it just, I've had ringing fits on my bench plate from the parts being so flat. So that was my first shot, was let's see if it works. And of course the engineers and everybody said, oh, it's not going to work. It does work. It works really well. And as we develop a product, it goes over 2.5, 3.5 years of cycling and testing and so on. The parts change, and oftentimes the fixturing would have to change. And so instead of bringing them back, setting up something that's all bolted together and doweled and precision, and then trying to figure out how to hold it, we'd simply print a new one. And as the part was updated, the fixture was updated. So as we send those back to the technicians, the file is updated and kept on hand, so that by the time it gets to the actual production, we've got the fixturing already ready to go for them. So lately, we just kind of run with this whole thing. We get a lot of custom printers as well. We have a client base where we use a lot of custom defined printers. We had one that there was an order. We were going to make probably a life cycle of maybe 300,000 printers of a particular flavor, and when we went to get a connector that would allow us to use existing cabling, we were told that it was going to take 1 million units for them to retool. Well, we didn't, to pay that and throw them away, or just to have the cost, just didn't set well with us. So we looked. We had an existing connector that if we removed made a little window so some clips would clear and pushed a couple pins out, we could make it work. So we needed 350 connectors. I made a quick little steel rule die. The next slide here that shows kind of the process that I used. I made a little core that would keep the connector from collapsing. Took some standard chisel point X-Acto blades, put them into a little holder, made a little guillotine press, and took it over to my toggle press and started punching these things out. By the next morning, they had their 350 connectors so that they could start testing right off the bat. What we found is, for about the first 4,000 or 5,000 printers that we delivered, they were made with the same process. We didn't have to go back and revisit this and say, okay, now what do? We simply used the little FDM tool that I created for the prototypes. The next slide shows a metering dispenser. We get a lot of college interns, and I love them because they have no concept of what it takes to machine something. So it's like in effect, it's like watching my 2-year-old granddaughter play. She has no limits to what her imagination will come up with. So this metering dispenser was a great idea. The problem was it was almost unmachinable. But the more we looked at it, we said, well, why don't we make it out FDM? Because it doesn't care if it's got all these weird little holes and sharp corners down inside there. Everything dropped in, and we made probably 60 of these little metering dispensers that the syringe clips in and out so they can load it, and it drops right back in, and it precisely dispenses whatever it is, either silicone oil or adhesives or whatever inside. This slide here shows encoder motors. We use encoder motors throughout our printers, and it's a tiny little thing. It's not much bigger around than maybe your thumb or your middle finger, and it's got all the electronics on the back of it. And I watched as these things were being destroyed, they would get like a nut or a little piece of scrap material and try to support the end of that shaft and press a gear onto it. Well, if it slips or moves, the little encoder disc gets broken or the electronics get damaged and it no longer works. So we were throwing these things away by the dozens, and so I made a quick little fixture. I just put a steel set screw up from the bottom that we could adjust for the right fit, and it actually, because I didn't have to machine it, I made some little over center features that the motor just clips into. It snaps in. We can take it over to a little toggle or arbor press, and we press gears on, and I put holes in it for the second version because they were putting a little steel plate on it, and they had some magnets, and it would just clip into the magnets, and it would align each time. We've probably done a dozen different motors this way. The next slide. This is another one of our interns, and his concept for this optical scanner, we check print density to see how thick the ink is put down, gives you a nice saturation base, and it's all done optically. The little unit that he envisioned here, in order to make it toggle and kind of flex and be adjustable, he had dovetails that were internal dovetails and long. This is about 6 to 8 inches long, maybe, and these long arms. And he submitted it as a machine part initially, and we looked at it, and we weren't sure if FDM was going to be quite accurate enough for something as precise as an optical scanner. But we thought, well, at least let's see if the concept's going to work. We put it together, and I mean, it measures down to nano inches. I mean, it's the sub-micron level of inspection on these things. So it actually, when we got it together, I had to take my hat off. It's very ingenious the way it worked. I have no idea how you would ever make it outside of something like FDM. This is a camera dock that we use. We use high-speed photography for testing fluid flow. In the big frame there, over on the right-hand side, you can see the gear section, and we have a hand crank and also a little electric motor, and we're dialing it down to sub-seconds of angle. Obviously degrees, minutes, seconds, and we're sub-seconds, I should say, just to see if it makes a difference, because if somebody were to park our printer on an uneven surface, we need to know if it's going to change anything. So we just sort of run a wide variety of testing with this. We could run it at 180 degrees if we felt we needed to. The frame out in the middle there is simply a threaded plate off of the flat plate that allows them to get underneath and attach things. And FDM worked great for this. Almost everything you see in this picture is FDM. It has a camera mount on the left-hand picture there. You can see the microscope camera, and even it sits on a fully adjustable FDM camera base. This is some detailed shots. One of the things that we heard over time about FDM was because you soak the material, some of the support off in various materials, it absorbs moisture. So therefore, the thought is, well, it obviously must leak. If you made a big box out of it, it's going to leak. We're putting silicone oil into this chamber, and it's dripping down in there. I took a little methylene chloride and just brushed the inside of it to seal this piece, and it might as well be Tupperware. It really seals. There's no leakage, no wicking up into the material at all, And this was a huge win. This was a joint project between NASA and Xerox and Portland State University. And with this apparatus, we were able to create the largest droplet of silicone oil. And that doesn't sound like a big thing to you or I, but to some PhD guys, they were just thrilled. They thought that was the coolest thing they'd ever come across. This slide, this is just a kind of a general sampling. We oftentimes will take one platform, we'll put new software, new controller boards in it, we'll put different features in it. And so while they're in prototype stage, it's always, you know, what do you do with them? You just lay them out on a table here? Well, they're portable. They go from one technician to another or to software people. And so the many pieces that this was going to be to try to fit the guts of the new controller boards and such, power supplies down inside there, was about 20 different parts. I said, well, in respect for the time that we have here, let's just get an FDM version of this thing and trial fit it. The right-hand picture, you can kind of see a long groove along that whole thing. That just drops down on the sheet metal back panel, and it holds everything, and the components slide right in. They put in with a couple of screws, and they can take them off. They can just detach them, set them aside, and drop them onto the next unit. And so, again, there was no point in trying to make this into many different pieces. We made this all one piece. And they listened to me. If you see the series of holes along there, one of the things they didn't want to wait on was me to get the support off, because it usually takes a couple hours or so to soak it off. So they put little peek holes in there so that the solution would get into that groove and take it out of that groove quicker so they could get it, in their hands faster. This slide, even though this is sort of a real part more than a fixture, what it was we were proposing a new paper path. And, of course, as it's inside the machine, the big round circle represents our drum, and this is the path that it needed to go to duplex, so it prints on both sides. And we have to have access, jam, drawers, and so on. And this was just a thin version. It's probably 6 inches deep by 2 feet by 2 feet, but it allowed them to take paper and run it down through there and flip all the little flippers and different levers to route the paper, to unjam the paper. And in one design review, we were able to completely set the architecture for our latest printer. This is my latest success story. I love this. This, as a machinist, as a tool and die maker, these little strips are probably 1.25 inches by 3 inches long, maybe, and they're vacuum chucks. With our print heads, there's over 1,200 orifices on the face of our print heads, and they all spit ink independently of each other. So there's this little flex circuit that goes on the back that has to be precisely aligned under a microscope and then fused on so that when the electrical impulses hit, it oil cans and spits out the droplet of ink. Well, in order to attach these little delicate flex circuits, we've machined these out of stainless steel in the past, and you've got a lot of deep drilling. You've got little real tight corners that you can't overcut, so or it would leak, and then we would water jet ceramic sponge. But since I've done a lot of thermoforming, I worked with Stratasys on thermoforming. I worked with some of the application engineers, and I got to thinking about this concept. What if I didn't use any support? I made a series of channels underneath, so that from the far, it progresses from the far left. This is the last layer up where we would attach our vacuum line, and it would go into the next piece over, and it's just a bunch of little standoffs that allow the air passage to go underneath there. The next progression then I would put a fairly coarse layer over the top of that, and then it prints up proud of that, because it has to stand several layers proud of the base piece, if that makes any sense, in order for the tails of the chip flex chip and things to hook on. And then lastly, the last 3 or 4 layers I printed very fine, so it's a nice smooth surface, and we just basically hit it on a lapping plate on some 1200 or 1500 grit sandpaper, just to take the fuzz off the top layer. They're cleaned in deionized water, and we use them in our clean rooms. This takes an hour and 5 minutes to print. The last series of these units I made, they ended up 36 hours a piece to machine them and water jet them and assemble them, and they never were really what we wanted. These worked so well. I was really proud of this accomplishment. The little rectangular holes that you see about a third of the way down, those are microscope holes. We look through a precise microscope at some fiducials, and we have to line that all up. And this aligns them as well as anything we ever machined. This just kind of, the very far left-hand slide, when I was working with the application engineers on thermoforming, because basically what we do with thermoforming, we're making little transparent shields or holders for sub-assemblies. Our heads are put together and they're dropped into little dishes, basically, and for protection, and then sent on to the next site. So we make a lot of thermoformed covers and holding apparatus for either production line or for our sub-production line. When we didn't have, Stratasys didn't know, we didn't know what the magic number was for putting porosity in it. How much is it going to take in order to suck through it? I know when I made them and I had to drill all these 30 thousandths diameter holes, it was always a headache. You could spend a lot of time shaping a mold, and then when you went to drill the holes, you'd break the drill, and you'd have to grind it off or get it down flush and start another one right in close to it, and that took more time than building the mold. So this way, it builds it with porosity. So the top picture, to go back to that, I put a light bulb behind it. You could literally read a newspaper through our first couple of attempts. And what we found is it doesn't take much porosity for it to be the best thermoform material you'll ever use. The picture on the bottom there, those are head covers that snap on. They actually have an undercut in them. And all of the packaging people said, well, you can't thermoform something with an undercut in it. It just isn't going to happen. You'll never get it off. Well, I don't like to be told that I can't do something. I am a little hard-headed in that way. So the ends of this come loose. So you would thermoform down over these 4 strips. When the strips come off, the ends just come right out of this piece. I push them towards the inside. It pulls them loose from the undercut. And so when we assemble these heads, we instantly could snap these clear covers down over the top, and so they wouldn't pick up debris or grit or any fuzz in the air, because they're put together in clean rooms, and then they're transported out onto the production line. And somewhere between the clean room and the production line, they were getting dirty. So it was a huge win, even though it was a pretty simple fix from my standpoint. And, final thoughts. Various people, they get ready to retire. They do something of note. They want some cool wall mount switch plate for their light switches in there that signify that they're part of a particular group. We knock these things out when we have space on the machine. Our site president happens to be an antique airplane collector. He has a Grumman Hellcat. I talked with one of the applications guys back in Eden Prairie. They found a model of that. They kind of digitized it. We made a scale model of that to put on his desk, and he was thrilled with it. But he's like, I want a nameplate made out of this. So we made a nameplate, and on his desk, when all the hot shots from wherever come in to visit with him, his nameplate that could be polished brass is FDM, and he believes in that. So far I haven't found anything I can't do with FDM. I believe in it. I started opening my mind to just, if I'm doing it this way and I'm machining it, how can I make my life easier? One thing that I think is really important to get across is when I log the job hours down, it might not look a lot different to do it in FDM or to do it in a machine, but the possibilities are more, number one. But number two, the same 36 hours that it took to do it either way, I'm not standing in front of a machine. So while I push the button and I'm making something that takes 36 hours, I'm spending 36 hours out cutting aluminum or something that I have to cut, that there's no other way around. So I'm doubling up my time, which makes my boss real happy, but it also just makes better sense. Sometimes what the engineer wants, you have to push back as a machinist and say, I can't have sharp corners here. I can't go 4.5 inches deep with an 1/8 inch radius in the corner. I can't, put this hole in from the side in a blind cavity like that. Well, that's where I want to put the bolt. Well, you're going to have to put the bolt someplace else. With FDM, it doesn't really matter. I mean, if you can get support to it, you can wash it out of there, and if you can get a tap in, or they can screw a self-threaded tap in there, the options are open to them. And our engineers have really embraced that. They design. We have a whole design phase. We do a feasibility study, and then we have an architectural review of a new proposed printer. The third phase of that, our upper management calls it FDM mock-up. And that's kind of cool. They don't call it a 3D printing mock-up or an RP mock-up. They call it FDM. They call it what it is, and they're so sold out to that it would be hard for me to try to get a different process in here. That's about all I've got.
Thank you, Duane. It's amazing all the things you were talking about, all the ways you can think of to use this technology, and how you guys in the Xerox model shop are really pushing the use of FDM forward. So that's great. Thank you. In a minute, we'll take any questions that you may have, and if you think of a question in the meantime, be sure to submit it through the Q&A panel. I wanted to let you know that after the event, you can download a couple of the stories that Xerox has using Stratasys FDM systems, as well as a copy of the slides and the recording of this webinar at the URL you see on the screen, stratasys.com/webinar_Xerox. All right, so let's get on to the Q&A. We've got a couple minutes here to get some questions through. It looks like a few questions have come in. We'll try to get through most of these before our time runs out. So here's one. Let's see. Looks like George wants to know, Duane, how did you finally convince the higher-ups to purchase the system in the first place?
Well, that was the easy part. When they totaled up the checks and they saw $1.6 million, they knew that we could. By doing it ourselves, we've always invested in technology, and so that was an easy sell. When we presented a $200,000 solution to that, it literally cut it down to about $870 the next year. So it almost cut it in half by by the $200,000 investment.
That's great. All right, Wendy is asking, what materials do you mostly use for your parts, and are they strong enough for what you're using them for?
That one always surprises me, because we kept, my dad was kind of old school, and I tear things apart that he's built years ago. It's got 20 nails when 3 would have worked, and I think we kind of took the same approach. We had to make everything really big and thick, and we went with polycarbonate for our fixtures for a long time. We had ABS, and then polycarbonate was kind of what we wanted to use. And since the new ABS M30s come out, we also make an awful lot of fixtures in that. And then we've upgraded our Titan to a Fortis ET now. And with that, we invested in Ultem, because we have a lot of heat and chemicals here that Ultem was just the perfect fit for. So if it's something that maybe end-of-arm robot tooling, or something that may be around heat, or it's going to be have weight hanging on it for any length of time, we'll go with Ultem. But any of those work just fine.
Okay, great. We'll take one more question at this point. John wants to know, do you do any finishing to your parts, or coating, or anything like that?
Well, we do paper path parts, and so it's always fun to try to get paper path. It can't be too glossy, and it can't be too rough, and so most of what I do is just sealing parts for it. Like when I talked about the silicone oil and so on, I'll just use like a methylene chloride or MEK or Weld-On or something, and we'll seal the parts. But I also have sealed them. I've used cyanoacrylate and baking powder and sanded, finished them that way. I find that probably if I'm gonna need something that has to have a particular surface finish to it, those are some that I will send out and just have finished at a service bureau. That's from my standpoint here, just because I'm kind of the Lone Ranger at times, and so that ties up my time that I could, I don't mind paying for that service. But it does finish pretty well, at least. It finishes well enough. If you were going to do a display model, there's probably other ways of doing it, to be honest.
Yeah, definitely. I know I've heard other customers doing, finishing, sanding, and chrome plating, or electroplating, and those kinds of things too. So there's definitely a lot of ways to finish things. So it depends on what your need is.
Yeah, exactly. We do so few display models. We're looking at function and fit, and it's probably the very best in that regard.
Good. Thank you. Well, it looks like at this point our time is about up. If we didn't get to your question live on the call, we'll be sure to follow up with you via email after the webinar. Thanks again, Duane, for your great insights, and thank you all for your attention during the presentation. Now I will turn it over to our operator, who will close out the event. Thank you. Bye-bye.
Hello again. This is Bill Koenig. As I mentioned earlier, because this was a pre-recorded presentation, any questions you submitted will not be answered today, but will be passed along for answering. Also, if you began listening after the presentation began, the entire webinar will be available for replay at 4 this afternoon Eastern Time. You can access it by using the same sign-in link you used to join us now. Additive manufacturing is receiving a good deal of consideration these days, as interest focuses on what many people consider to be a new technology. However, Advanced Manufacturing Media's parent organization, SME, has been involved with this innovative and developing technology for decades. For example, SME's Rapid Technologies and Additive Manufacturing community has been serving and supporting the technology for 25 years. Additive manufacturing also receives extensive coverage in Manufacturing Engineering magazine. Past articles may be found in our digital archive at sme.org/digitalmemag. Plus, you can find the latest rapid and additive manufacturing news and information at our website at www.advancedmanufacturing.org. Upcoming SME events include WestTech, September 15 to 17 in Los Angeles, and CMTS, September 28 to October 1 in Mississauga, Ontario. That's near Toronto. Thanks for joining us today. We hope you found the presentation informative.